Happy Easter, everybody. So I'm here at Stony Brook University. The professor from Stony Brook University is here.
I'm Jacobus Verbaarschot, a physicist at Stony Brook University.
He's been teaching me relativity for the past few weeks. We've been making some good progress, and I'm pretty excited.
Pace, you have to change the derivative. And that's a non-trivial thing. So you have to think what it means that there is a derivative.
What does it mean to take the derivative over like a curved surface?
So if you have a vector like this, and a derivative is normally the definition, and you take a vector and a little bit, so that is, say, V alpha, and here is V alpha, plus delta V alpha. So you do it with a normal definition. Normal definition, x plus delta x minus f of x divided by delta x. That when delta x is small, it becomes the derivative. But now when there is curvature, the vector also changes because of curvature, and you have to take that into account.
Oh, I see.
So the derivative becomes actually a much more complicated object, because you have to take into account the curvature.
Right.
What enters into the geodesic equation is this derivative that takes that into account. And what you know is the derivative has a number of properties, like it is linear. What we know is if there's the new derivative, so we want to find the new derivative, and the derivative of lambda times a vector should be the derivative, lambda times the derivative of the vector. It should be linear. It should obey Leibniz rule. You know Leibniz rule?
What is that?
That if you have the derivative, say, of two vectors, that is the product rule, really.
Oh.
Plus, and then del of V alpha times W beta should satisfy the Leibniz rule. It should, when you have a function, and not a vector, just a function, then this derivative should be the ordinary derivative. So this should be the function. So it should have a number of rules, and these are all the rules. There are some also rules when it commutes with a contraction. So if you have a tensor here, alpha, mu, there are betas here. So this is contracted. That is the same as first differentiating the tensor and doing the contraction afterwards. But this is kind of an obvious thing. The Leibniz rule is really the main thing. That's the real non-trivial thing. So the question is, what can this derivative be in general?
And I feel like given only those three rules, it could be any number of things, right?
No, not any number of things.
This isolates it to just one definition?
No, it can be many things, but not any. So what we can show is that if this is, say, the mu derivative is equal to, and that's, I think I should get my conventions right. let me put them as lower indices because that's in my note. It is the ordinary derivative, and then there is another term. And the other term is C gamma mu alpha times V gamma.
So this other term could be made to go to zero when the surface that we're working with.
No, it's in flat space. This is zero.
Right.
But we are not after flat space in general relativity, and these can be kind of arbitrary coefficients. They are related to the metric tensor, which depends on space-time. And what is important is that this doesn't contain any derivatives of v lambda, of higher derivatives. It only depends on the vector at point x. And this is the most general kind of generalization of derivative you can have. So this is the derivative of general relativity. And
can we express that coefficient in more detail?
We can express it in terms of the metric tensor. In one case, if this alpha derivative vanishes. And that is the case for general relativity. This is called metric compatibility. So if this is the case, you can find an analytical expression for these coefficients. And it is basically straightforward how to do that. And it's a little tricky. I even don't remember it exactly. And that is a vector in general relativity. So the invariance group is arbitrary coordinate transformations. So they're not simply Lorentz transformations, but it's an arbitrary change of coordinates. And that's important also from with and when you have a more than one index, a tensor, then each of the indices of a tensor. So if you have a tensor, T alpha beta, that would be dx alpha, dx alpha prime, dx beta, dx beta prime times T alpha prime, beta prime. Do I get T alpha beta? I did not get the indices right. So the indices are here, and this is alpha and beta. Now they are right. So and this is the primed ones. So this is a tensor in general relativity. These are the transformation properties. In special relativity, this is a Lorentz transformation.
Partial x alpha over partial x alpha?
Excuse me?
This is partial x alpha over partial x alpha?
No, sorry, that's a prime. And there's, did I write it out the right way? So this alpha and beta, these are the primes. Didn't write the primes in the right way. So one should be always a contraction between upper and lower indices. So that's the concept of vectors and tensors. It works the same way as special relativity, but now in special relativity, these were Lorentz transformations like this, and L beta prime beta. And now they are arbitrary coordinate transformations. And all equations of physics should be invariant with respect to arbitrary coordinate transformations. So nothing should depend on the coordinates. So the first thing we now know how this acts on a vector. So the first thing you have to know is how this acts on a tensor. So you have, in general, delta alpha t, say, mu nu on a tensor. And how you prove that is you act with delta alpha on t mu nu times a vector nu. Now this is again a vector because this is contracted. So we know how this works. So that is d alpha of t mu nu times v nu. And then the second symbol, that is c. This is just a vector. So that is c, say, beta alpha mu. And now this is the tensor. So this becomes t beta nu v nu. Sorry, there's a plus here. So on a vector, it behaves like this. But we also know that this satisfies a Leibniz rule. So that is equal to d alpha t mu nu times v nu plus t mu nu times del alpha of v nu. This is what we want to find out what that is. That is d alpha of t mu nu times v nu. And here, this is now t mu nu. This is again a vector, so that is d alpha v nu. And then we have this vector. And we did not really, this now has an upper index. And here we only showed it for lower index. Then actually there's a minus sign. There's again this symbol. It is an upper index. So that means there's a beta here. Now the beta has to be here. The nu has to be here. And the alpha has to be here. And now we know that this should be equal to this. And bracket closes here. So we're almost done. So this is the object we need. That is the covariant derivative of a tensor times, I still have right v nu. That is equal to, here we have the ordinary derivative. That is d alpha t mu nu v nu. It's the ordinary derivative. Then here we bring this to the other side. So we have minus t mu nu times d alpha v nu. That is this term. Then we have this term, that is c alpha mu beta times t beta nu times v nu. And finally, we have this term. And did I forget something here? Yeah, the brackets should be here. They were correct. So I bring this to the other side. That becomes then t mu nu c nu alpha beta times v beta. And this is equal to, because this cancels against that, that is d alpha T mu nu times V nu. And now we have two terms with these T's. So that is C beta alpha nu times T beta nu plus, and now we change the names of the indices. I call the nu a beta and the beta a nu. These are just dummy indices, so that doesn't matter. So I call this a beta, then this should be a beta, and the beta is a nu, so that is V nu.
Why do we change the indices? Is it just for ease of writing?
Yeah, I come to that in a second. So this is a nu. So why we change the indices? Because now everywhere there's a V nu. And this is true for all V nu. And that means that the coefficients are equal. And that means that we have derived a tensor, the derivative of a tensor, which is equal to the ordinary derivative of a tensor. That's this one, plus C alpha mu beta times T beta nu. There's this term, and there's a second term that is C. Okay, where did my beta go? So I erased indices. I have here alpha, my alpha disappeared. This, okay, we have to check it again. I erased two things too fast. So here you see that you have alpha, beta, there's an alpha, the beta is contracted, but I wanted to make this a beta, so we have, oh, I didn't write the T mu nu, okay, so we have T mu, and the nu became a beta, and here I have the C, the nu became a beta, and the beta became a nu, so this became an alpha. So I didn't copy it right. Okay, so what do we get here? C beta alpha nu times T mu beta. And if you look at it, what you do is, this is the same as a vector, so the mu, that now becomes a beta with this symbol. And in this case, the nu, this remains a mu, and now this is treated the same way as a vector. And this is how a covariant derivative acts on a tensor. And if there are more indices, there are more of these same type of factors.
But we're mostly going to be dealing with 3 indices, right? Or 4.
Yeah, usually there are only a couple. Usually we only have to deal with the metric tensor, which has 2 indices, and covariant derivatives of the metric tensor. And now, this is still arbitrary. And now we introduce the Christoffel symbols by these things. And we use them when, and in fact we use minus sign here, when the covariant derivative of g mu nu is equal to 0. So maybe I should put a minus sign there. That's better.
Beta, alpha, beta?
Sorry, alpha nu.
This feels like just reassigning it a new symbol.
And it is, it's not really, up to now we work with a more general definition. So these are derivatives for any choice of these coefficients. Now we solve these coefficients such that this relation is satisfied.
Oh, right.
And then the name of these coefficients is minus gamma beta alpha nu. And that gives you an explicit expression for these coefficients in terms of the and
What do the subscripts on the nominal symbol represent?
Just partial differential, partial derivatives. So it is like this. Here you see it. D mu is the normal derivative, and then there's some linear combination of the vectors. Okay. So you do it in the same way, and when you differentiate that, you have these extra terms, which makes life very complicated. Because and the complication is because there's just many terms. If you count the number of terms, each of these indices runs from 0 to 3. Oh. So how many do you have then?
Well, since that means since we have 3 indices and each of them run from 0 to 3, which is 4 for each time index.
How much? How many?
Oh, 4 factorial, so 20.
No. Okay. Each can run from, can have the values 0 to, there are 4 for each. So there are 64 of them.
That sounds like it wouldn't be very nice to manage.
No, it is. You have to do work if you solve problems in general relativity.
But of course.
So you have to work hard. And these are ugly equations. But there are computers who do that for you. And they have some symmetries, but actually not many. What we will see is that C is C gamma beta alpha, which reduces.
It's on half about?
Yeah, so here there are 4 plus 3 plus 2 plus 1. That is how much? 12? 4 plus 3 plus 2 plus 1, that's 10. So there are 40 instead of 64.
Okay, that's nice.
Yeah. So what you can show is that the following, that gamma sigma mu nu is minus a half g sigma rho of d rho g mu nu minus d mu g nu rho minus d nu g rho mu. It's a complicated combination, and that follows when this derivative of g mu nu is equal to 0.
Okay.
Do you want to understand that?
I think I've derived it before, but with Giovanni, I might as well derive it again. Why is this true, given the other relation as well as this relation?
So why we didn't have another relation?
Oh. That one over there?
This is a definition.
Oh,
That's really the definition. So if you write this out, what is this? This is d alpha g mu nu minus gamma, and I use my notation, mu nu g, and I better use the notation of my notes. Okay, I have to change notation. So what I'm going to look at del mu g nu rho. That is d mu of g nu rho, the normal derivative, and then minus gamma, and I call that lambda, and then mu, and here mu times g lambda rho. So this, the first index is contracted, and then the second index of g is contracted. The first remains what it was. There's a lambda here, there's a mu here, and we have still one index, that is, what is it, the rho. So this is the derivative, and we require that this is equal to 0. And now we want to basically eliminate this. Kind of, you can see that this can be done because you have to act with the inverse of this, and then you act, this is the inverse, you act on this. But it doesn't quite work because these are different matrices. So you have to do some tricks. And what you do is you do a cyclic permutation of these things. So you change, this becomes a nu, this becomes a rho, and this, so this becomes a nu. So the mu becomes a nu, the nu becomes a rho, and the rho becomes a mu. And you do that everywhere here. So the mu becomes a nu, the mu becomes a rho, and the rho becomes a mu, minus gamma and lambda. The mu becomes a nu. It is very easy to get confused when you do this. And here you have g lambda, and the rho became a mu, minus gamma lambda. The mu became a nu, the rho becomes a mu, and the nu becomes a rho. So we have c rho lambda, that's this equation. And now what you can do is you can look at the following combinations. In fact, you can look at, if you now look at the derivatives, so we have here d mu of this, d nu of that, and we want to do it once more, that mu, so the next step we want to, here, we want to do one more cyclic permutation. So in this case, now nu becomes a rho, rho becomes a mu, and mu becomes a nu. So this becomes del rho g mu nu. Yeah, that's what I have. Is equal to the nu becomes a row, so that's a row. G, the row becomes a mu, and the mu became a nu, minus, here we have gamma lambda. The nu becomes a row, the row becomes a mu, times G lambda nu minus gamma lambda. The nu becomes a row. Okay, cheers. The nu becomes a row, the mu becomes a nu, and here we have G, there's a row, and the row became a mu. So we have made 3 different equations. And now you are going to add and subtract them.
That doesn't sound.
Okay, I need page 55 of my notes. Where's 55? Oh no, 54. I have that here.
Wait, can we say that GAB equals GBA or something like that?
But that, oh yeah, the metric tensor is symmetric.
Okay.
So now what you can do is, the reason it's symmetric is that the metric tensor comes into the metric. And so you have that ds squared is equal to gx again into the second derivative. But they are not there to define the curvature.
Okay.
And you can show that, and we did not show that. Also for the derivatives, you could have more complicated combinations, but derivatives enter not in the game. The proof is in my notes,
Okay.
but you should read that and go through that.
What set of lecture notes?
In the ones that are on the web page, somewhere here.
Yes, but there were multiple. Very interesting. One final question. What do we mean when we talk about curvature exactly? What is like a rigorous definition for curvature?
What we mean by curved is like sphere. A sphere is curved.
Well,
what we mean in maybe a simple way is if you draw a triangle of a sphere, the sum of the angles is not 180 degrees. So that's curvature.
Is there a way to quantify curvature? Like, can we say that one surface is more curved than another?
Oh yeah, that is this tensor. This is the curvature scalar. For a sphere, this is actually a constant all over a sphere. In flat space, this is 0. On a cylinder, it is also 0 because this cylinder is not curved.
Okay. Do you think it would be feasible to cover that next time?
We can do some examples involving curvature, and for example, a sphere. And we didn't discuss parallel transport yet, so we have to.
Is that the natural next step?
That's one of the steps to understand geodesics, for example.
Okay.
So you need parallel transport.
So maybe we can cover that next time?
Yeah, we should cover that.
Okay.
But I went to that to see where we are going.
Yeah, it's always important to
Yeah, so that's the first goal to understand, to go to the Einstein equation, and after that to understand the solutions of the Einstein equation.
I may need to learn a little bit more math because I'm not experienced with partial differential equations yet. So
You always need partial differential equations in physics.